In this video we will discuss how to verify whether two given vertices S and R lie on the same cycle in a given directed graph. Given a directed graph, we represent this graph as vector of edges, and I call it adjacency lists, which is ADJ. Edge struct has integer neighbor and integer w. So neighbor is just a vertex to which this edge goes to, and w, integer, holds some additional information that might be useful to solve some problems. We need to write down a function that is called same cycle. It takes as parameters two integers s and r, and it returns true if s and r lie on the same cycle in the graph. What does it mean, a cycle in the directed graph? For example, vertices 2, 4, 11 and 7 form a cycle because there is an edge between two consecutive vertices, and if you follow these edges you will come back to the same vertex. So this is a cycle. 4, 11, 11, 4, 4, 11, 4 is also a cycle. Another cycle is 2, 4, 6, 8, 7, 2. This is also a cycle. Another cycle in this graph is 9, 4, 10 and 9. So if we are given, for example, s equal to 2 and r equal to 11, then because there is a cycle on which these two nodes lie on the same cycle, this algorithm should return true. Whenever we talk about cycles, cycles are easily recognized when you run DFS. And in some cases, you do not need to run the entire DFS, you only need to run DFS visit. Because we really need to verify only two nodes whether they lie on the same cycle, we can run DFS on S, and whenever we discover a cycle, and a cycle is discovered whenever there is a vertex encountered and color of that vertex is gray, that means we found a cycle. Then all we need to do is backtrack that cycle and see if there is vertex R also lies on that cycle. However, the problem is more complicated than that. Now let's look at this specific graph example. I'm going to run DFS visit on s equal to 2, and let's assume that r is equal to 11. And I'm going to show DFS visit parents and color of each vertex as I go. So I start DFS visit on 2. Every vertex right now has color white. I'm not writing it down, but let's just remember that every vertex right now has color white and has parent itself. When we start the first visit on 2, we color it into color gray. I'm gonna use green, it has the same initial letter. So this is green, and let's assume another thing, that all the vertices are ordered in adjacency lists in increasing order. For example, if there's two edges from 4 to 6 and 4 to 11, then 6 will appear before 11 in that adjacency list in increasing order. So 2 has only one edge to 4, so it will visit 4. So 4 right now is green, and 4 will set parent 2. From 4, in adjacency list we'll visit 6 first before 11, so 6 will be set to green, and parent of 6 will be 4 because we discovered 6 for the first time from vertex 4. From 6 we will discover first 8 because this is less than 11, so it will occur in adjacency list before 11. So we'll set 8 to green, and parent will be 6. After that we will discover 7. This will be green, and parent will be 8. And after that, we will, from 7 adjacency list, we'll encounter 2 and we'll check its color. Its color is not white anymore, it's gray or green in this example. So if it is gray, that means this vertex has not finished yet. That means there is a path from this vertex to the vertex 7, and this edge from 7 to 8 concludes a cycle. Now if we want to check if this cycle contains R, and R, remember, is 11 in our case, we can backtrack parent array starting at this vertex, at vertex 7. From vertex 7 we discovered 2 and discovered that 2 is not white, it is gray. So we start backtracking from 7. Because vertex 2 has parent 2, so if you try to backtrack it from 2, parent of 2 is 2, it will not go anywhere. So we need to backtrack from 7. Starting from 7, we're looking at its parent. Parent is 8, so we can go to its parent. Parent of 8 is 6, so we go to 4. To 6. And parent of 6 is 4, so we go to 4. And parent of 4 is 2, we go to 2. And while we're backtracking, we compare each encountered vertex with vertex R, which is 11. None of these vertices is 11, so we discovered a cycle. However, the second vertex is not in this cycle. At this point, we should not return false yet, because there might be another cycle on which 11 lies and S, which is 2, lies together. So this was case 1, found a cycle, but R is not on it. Now let's look what other cases we might have. So after we encounter 2, we call a special function that backtracks this parent array and finds that R is not there. It returns us with false, but we can continue our DFS visit, starting with this vertex 7. Because it doesn't have any other edges, that means that it returns. That means that we're going to set its color to black, because it finished with its children, so color of 7 is black, and it returns to 8. 8 doesn't have any more children, so it is finished. Its color will be set to black before finishing, and then it returns to its parent. This parent, this node, has another child, 11, so it's not finished yet. It's going to call DFS visit on 11, because 11 right now is white. We call DFS visit on 11. We set it to green and set parent to 6, because we discovered it from 6. And 11 will process its children also in increasing order. The first child is 4 and the second is 7, so it processes children one at a time. Now look what happens. It discovers 4, checks its color, it's gray. That means that there is a path from 4 to 7, and this edge concludes the cycle. So we need really to pass this vertex to the function that backtracks the cycle. So it starts backtracking at 11, and it backtracks all the way to 4, and it can verify whether S or R, S and R lie on this cycle. And in fact, neither R lies on this cycle, but S doesn't lie on this cycle. In fact, we can make our job easier by just checking if this vertex 4, which is encountered as gray, is it our vertex on which we started our DFS visit? Because we started DFS visit on S. So we can check simply its parent. Is this parent is equal to itself? Because if it is equal to itself, that means it is our vertex on which we started DFS visit. But it is not vertex that we started DFS visit. That means it's not our S. That means our cycle that we found doesn't contain S. So we do not have even to backtrack it right now. So this case is 2. We found a cycle, but S is not on it. we can easily check this condition, whether S is on it or not, whether we need to backtrack or not, by checking parent of this gray vertex. If parent is equal to the vertex, then it is our original vertex on which we started DFS visit. If not, that means that we do not even need to backtrack this cycle, because this cycle doesn't have S on it. Okay, this was case 1, we're done. Case 2, we're done. What do we do next? From 11, we return right in here in 11, and 11 has another child, and another child is 7. It checks, it only calls DFS visit on 7 if 7 is white. But look at the color of 7. 7 is black. So we do not call DFS visit on 7 when we found 7 in the adjacency list of 11. That means that we return reset color of 11 to black, because we're done with its children, we checked its children, we set it to black, and we return to its parent. Parent is 6, so we return right here. Now 6 was done with both of the children, so 6 will set itself to black and will return to its parent 4. 4 is done with its is not done with its children. It checked only 6, but now it checks 11. Is it white? Do I need to call DFS visit on this child? No, it's already black, so we do not call DFS visit on this child. That means that we process both children and we set this vertex to be black, and we return to its parent, which is 2. This is parent 2. Parent 2 doesn't have any more children, so it will set color to black and it will return. Notice that this procedure, which concludes our case 3, might actually not find a cycle on which both 2 and 11 lie, even though that cycle exists in this graph. That means that we cannot really count on this method. Can we come up with something else? And indeed, we can come up with something else by doing the following. Let me erase all my colors for each vertex while I was visiting DFS visit. And now what I'm going to do is I'm going to run actually BFS on S. Right now, instead of running DFS visit on S, it was a seemingly great idea, but it doesn't work on all cases. So what I'm going to do, I'm going to run, what if I run BFS now on vertex S? How can I use that? BFS or DFS visit, whatever you want. But what we're doing here is we're going to mark all the reachable vertices, right? All the vertices that will be reached from 2 will be colored by black at the end of this DFS visit or BFS. You can use whatever you want. So let me write it down. I can run DFS visit on S or BFS. Let me try BFS on S. And as you know, BFS uses distance array, and what happens, it will calculate all the shortest distances and calculates parents of these distances. So if I run BFS on 2, BFS will set parent of 2 to 2, and distance will be set to 0. Then we'll go to 4. 4 will set parent to 2, and we'll set distance to 1 greater than parent, so to 1. And it will visit 6, so parent would be 4, distance would be 2. Here we have 6, distance is 3, parent is 8, distance is 4. This is already visited, we do not reset it, we return here, visit here, parent 6, distance is 3, and this is visited, so we're done. We return here. This would be our parents, and this would be our distance. What we really need to do here is we would like to backtrack parent array starting with R. So we run BFS on S, this S, first parameter. Now what we want to do is backtrack parent array and starting with R. We start with R and backtrack parent array. And as we backtrack parent array, we set each edge. Set each edge W weight to -1. So let's try to do it with our example here. Here's our R11. We backtrack parent array. We're looking at its parent. Parent is 6. So go back to 6. Find adjacency list of 6. Traverse adjacency list of 6. It has 2 edges there. Find the edge that goes from 6 to 11 and set weight of that edge to -1. So we're using this W to hold extra information. All W's were initialized with 0. Now this edge 611 has weight set to -1. After that, we call the same backtracking function on parent of 11, 6. 6 has parent 4, so it will go to 4. And here we need to go through adjacency list of 4. It might have more edges than 1. Find one edge that has neighbor 6 and set the weight of this edge to -1. Then we go and recursively call it on parent of 4. Parent of 4 is 2. So we look through adjacency list of 2, find the vertex 4, and set the edge to -1. How does it help us? What we did is set all the edges to -1, all the weights of edges on the path from S to 11 to -1. That means there exists a path from 2 to 11. Now to find out, and let me mark this path with red edges. Now we would like to know if there is a path of different path that doesn't include these edges that we marked, that takes us from 11 to 2. Is there such a path in the graph? If there is a path from R to S that has edges whose weight wasn't set to -1. So step 3 of your algorithm, you need to run BFS on R and make sure that only visit through when you're looking at adjacency list. Not only you need to look at adjacency list, you basically set parents array of your for running BFS on R, and you reset distances, but you do not touch weights. So while you're running BFS on R, let's say you're looking at adjacency of R right in here. It has two edges. So it looks at this edge and checks if this edge has weight of -1. No, it doesn't. So you can actually put this, and it is also has distance infinity because you reset all these distances. Let me remove this. These were different numbers. We need to reset distances and parents after that because we're running a new BFS with new source, which is R, and parents and distances will be reset. So parent of 11 is 11, distance is 0. Then it looks at 4, and it looks at this edge. Looks at the neighbor, neighbor is 4, distance of 4 is infinity, good. What about this edge? Edge doesn't have weight -1, so it is also good. That means that we can put 4 into the queue in the BFS. So we put 4 into the queue and we set a parent of 4 to 11, distance to 1. Then we look at the next edge of 11. We look at the neighbor 7, its distance is infinity, and also edge, weight of this edge is not -1, so we can put 7 into the queue. We set a parent of this 7, 11, and we put distance, set distance to 1, and we put 7 into the queue. After that, we process in 4. In 4, we have two edges. It first looks at the edge 6. When it looks at edge 6, 6 has infinity distance, but W is -1. That means we shouldn't take this edge. We're not gonna put 6 into Q. So we're looking at this edge. This edge doesn't have -1, so but its distance is not infinity, so we don't put it in the queue. We return. Okay, and then we proceed to 11th. In fact, it's not the correct order I was processing, but 11 also has child 7. I actually already did it. Sorry, getting confused here. Okay, so 4 is processed as children. Now we're processing children of 11. So 7 has edge to 2, and this edge doesn't have weight -1. That means we can put 2 into our queue. We can set its parent to 7 and distance to 2 and put it in the queue. And then now we finished with the 11, 4, and 7 in our queue, and we're working with vertex 2. Vertex 2 looks at its adjacency list. 4 doesn't have infinity distance, and also weight is -1, so we're done with 2 and our queue is empty. So after running this BFS on 11, what we will have is we set parents again and we set distances, but we only used edges that didn't have -1 in its W. What happens now? How do we decide whether S and R do lie on the same cycle? Well, step 4, after this DFS, check distance. Check distance. Distance of what? Since we ran it on R, could we find path from R to S? If distance of S is not equal to infinity, then S and R indeed lie on the same cycle. That concludes your algorithm. Let me just wrap up our logic of this algorithm. First, we found one path from S to R and set edges on this path to -1. We set weights of edges on this path to -1. After that, we ran the second BFS on R to see, can we conclude the cycle? Can we find another path that goes from 11 to 7 through the edges that are not marked with -1? That means that we found one path from 2 to 11 and another path, different path, from 11 to 2. And these two paths concatenated will produce you a cycle. So in this case, return true. If after you run BFS on S, You also need to check if distance of R is infinity. That means you cannot even reach from S to R, so you should reach on false.